resources. There is our Unity slideshow. Your choice board has been posted. Very exciting. There's lots of fun activities for you to look into to get some extra credit or to be able to trade out some vocabulary or an assignment you don't feel like doing. So take a look at that choice board when you get a chance. But for today, let's stay on schedule. We're going to lesson 17.2. We talked about Chuck the other day. We talked about natural selection. You got to do a really fun natural selection simulation. If you're not finished with that, you'll have time to do it this week because we have all these half days. But today we're looking at some evidence for Charles Darwin's theory of evolution. Evidence for evolution comes from a lot of different places. It comes from the fossil record, radiometric dating, genetic information, the distribution of organisms, and anatomical and developmental similarities across species. We know that the fossil record is not a complete record of ancient life, but the fossils that have been discovered do give some really great information about how organisms lived a really long time ago. So, when fossils are discovered and they're able to be studied, if they have been preserved and they haven't been destroyed by nature over time, they do give us a really good insight into the evolutionary changes that have taken place in living organisms over all this time. Another piece of information that adds to the evolutionary knowledge that we have is biogeography. And biogeography simply refers to the study of where organisms live now and where their ancestors lived. This does provide evidence for two theories. One is the Pangea theory, which is the supercontinent. You may have learned about this in Earth space science, but if we take a look at the continents, they roughly fit together like pieces of a jigsaw puzzle, which gives evidence and supports that continental drift is taking place. Not just the puzzle piece aspect of it, but if we look at the way similar organisms are distributed across the planet, you can see that where the continents lined up, there are a lot of organisms that share similarities. So it's pretty cool. That's the distribution of species that supports not only Pangea, but also evolution. Distribution of species can also be looked at when we think about how the diversity of organisms are distributed across the planet. When we look at different anatomical comparisons, there's a few terms that come into play here. You have homologous structures, vestigial structures, and analogous structures. Now, homologous structures are anatomically similar, even though they have different functions or different jobs. And what this does is it supports the idea that divergent evolution took place, and at some point they may have shared some common ancestry. The really famous examples are the radius and ulna and wrist bones of a human, cow, cat, horse, whale, bird. They all share some very similar anatomical features, but we know that they have different functions. Our radius and ulna does something very different than that of a bird or a cat or a whale. So, just a very interesting look at homologous structures. Vestigial structures are structures that may have been left over. They don't really serve a purpose now, but they do give some insight into the evolutionary past and the ancestry of organisms millions of years ago. You've got some fish that live in caves. They do have real eyes, but they can't see. So they have this kind of useless eye here. Why is that there? Why is that left over from an evolutionary past? Whales have pelvic limbs. Humans can wiggle their ears. Some of us can. These are all indicators that these features might have been useful in our past ancestry, even though it's not something that we use now. And finally, analogous structures are kind of the opposite of vestigial structures. They don't share a similar function They do I always say it backwards. They do share a similar function, but they do not share the same evolutionary history. And when we look at all of these little swimming structures, your whale flipper, your feet turtle feet, your fish flippers, your penguins flippers, okay? Is that a turtle flipper? I don't know. But they do all get used for swimming, but they don't share an evolutionary history. So those are analogous structures. We also have embryological development that can give us some insight into the developmental history or evolutionary history of organisms. This has always been fascinating to me. When you look at the embryos of fish, reptiles, birds, humans, we all kind of travel through our evolutionary timeline during our development. So, little tiny embryo is going to have gill slits. We're going to have a tail, like a little, our spinal cord creates a tail feature. We've got this big bulbous eye, and our head structures look very similar. And as we go through development, it's almost as if you travel through all of the stages of your evolutionary history. So, just some of those features lend themselves to support evolution. The big one right now, that wasn't known during Charles Darwin's time is the genetic component. When we look at genetics and molecular biology, DNA, the universal genetic code at the molecular level, there's overwhelming similarities in the genetic code of all organisms, along with homologous genes and molecules that provide evidence for common descent. So you can look at these graphs here and you can see the percent of nucleotides that differentiate one organism from another, and also how similar some organisms are in terms of their molecular DNA. All right. Your assignment tomorrow is going to be to read about the amazing life and careers of Peter and Rosemary Grant. I'll get into that tomorrow. And I think that's where we're going to stop lesson 17. So I hope you're doing well. I will talk to you later.